So while you were working, I dropped off a second VSEPR theory sheet. And the information up at the top is basically the same as the information on the sheet that you had when you were doing your ed puzzle. Just kind of giving you some background. Big thing here is to remember we are always paying attention to the central atom and then kind of working our way out from there. The ed puzzle brought forth two different ideas here. They talked about the molecular shape, which is where the atoms are, and that's like the little balls in your model kit. So where the little balls are versus electron group geometry, which is more like where the sticks are. The electron group geometry is where the electron groups are. And ultimately, we're going to be able to make families based upon the electron group geometry. So to help you out with this, we're going to have you build a few different things. There are really only three families that we're going to have to worry about in here. There's the linear family, which is what we're going to have if we have two electron groups. And that wasn't really dealt with in the ed puzzle, and I'm not really going to need you to build this because, on the whole, people don't have any trouble with the linear family. It's the family of things that are in a line. If you have two electron groups coming off of a central point, in order to make them as far away from one another as they can possibly be, we just have to put everything in a straight line. So the linear family is built on that situation right there, the idea of having the electrons arranged linearly from one another. And there's not a lot of variation in this group, because even if you remove one of the atoms at the end and create an unshared position, so even if we take this one off, you still have a linear molecule. So like I said, the linear family is very dull. Everything is just linear. Our next family is the family with three electron groups. So I'd like everybody to build themselves a three electron group family. And the secret to using the gray one is to look down the middle and find the hole you can see all the way through, and then don't use that hole. Use the other three holes. And you can just use the white ones to cap the ends off. So it should look like a triangle. If it doesn't lay flat, or it looks like a T, you need to move the sticks around until you make it lay flat and look like a triangle. So this is going to be our model that we use to represent the trigonal planar family. The trigonal planar family looks like that. And the other family we're going to worry about in this class is the 4 electrons group family. So grab the black one out of your model kit and fill up all the holes and create this character. And this molecule is going to be our prototype for the tetrahedral family. Now, drawing this thing is a little bit more of a challenge. So essentially, here's the perspective we're going to take for the purpose of drawing it. We're going to say that these three are basically on the surface of the paper. So here's the up one, the middle one, and diagonally down. So if you hold it such that these are parallel to your paper, there's essentially one coming kind of diagonally up and one going kind of diagonally down into your paper. Now that becomes a little difficult to draw, but chemists have a way of doing that. To say that it's coming out of the paper, we draw a triangle with the fat end pointing out to try to kind of make that look like it's coming up and out of the paper. And then we use some dashed lines to make it look like that one's going back and in the paper. So we have a three-dimensional representation of our tetrahedral family. And this is kind of a nice time of year to talk about the tetrahedral thing because it looks like the back scratchers that they sell at upscale department stores right around the holiday time, where you pick this thing up and you just kind of give your friend a back rub. So it looks like the back scratcher from an upscale department store, or if you would rather, a spaceship with 3 pod feet. And then it can land on the surface of the planet, and because it has 3 pod feet, the astronaut capsule is up and off the surface so it doesn't get stuck in the planetary goo, and it can take off again, and it has this nice little antenna for broadcasting information back to Earth. But somehow you got to get yourself a mental image of this thing. So go with spaceship, back scratcher, however you want to look at it. Your life will be easier in this little segment if you can visualize these 3 things. The yellow one that's linear, the gray one that's trigonal planar, and the black one that's tetrahedral. So those are our families based upon electron group geometry. If we go back to the grid that you filled in while watching your ed puzzle, we can hook together the columns that say total number of electron positions and electron pair geometry. And I'm going to take my highlighter and I'm going to highlight. So notice I made electron group geometry blue, and now I'm going to hook together total number of electron positions and electron pair geometry. Because these go together. And based on electron group geometry, we can actually divide these into families. And that's what we're going to do with your 2 crayons. Your first family is everybody who has 2 electron positions. Maybe we'll do this. Or sorry, everyone who has 3 electron positions. So grab your crayon. I'm going to take all of this. I'm going to color all this to say these molecules are part of the same family. And when you were doing the ed puzzle, when you had these 2 models built, I had you lay them over the top of one another when I came around to look at them, so that you could see that although the molecules look very different, if you tried to lay one over the top of the other, their electrons were actually arranged in a very, very similar way, and that's why they're part of the same family. Likewise, when you built the CH4, the NH3, and the H2O, and you had the sticks in place to represent the lone pairs, you hopefully noticed that all 3 of these molecules were basically built on the same structure as well. So they're our tetrahedral family, and we're going to color them a different color. And so now we just have to worry about what goes in each family. So starting with our trigonal planar family here, if we have 0 unshared electron positions, the molecule has exactly the same shape as the electron pair geometry. So if this number is 0, the molecular geometry is exactly the same as the electron pair geometry. Because there's an atom at the end of every electron pair, we can sort of see the position of every electron pair. So this one remained trigonal planar. In terms of the bond angles, this one I don't think you even really have to memorize, because if you can visualize this thing, you can figure it out. There's 360 degrees in a circle, and so if we take that 360 degrees and we divide it into 3 even pieces, every one of those bonds represents 120 degrees of our trip around the circle. Now, the shape of the molecule is actually determined by the combination of shared positions and unshared positions, because essentially the unshared positions are going to end up being invisible. So if we lump bonding pairs and lone pair positions together, that's going to get us to our molecular geometry. So we're going to hook all 3 of these boxes together, because that's how we're getting molecular geometry. So if we take our trigonal planar molecule and we make one of these positions become unshared, what we're doing is we're removing one of the atoms from the end of that. And so now we have 2 shared positions, 1 unshared position, and the unshared position is essentially invisible because we can't see the electrons. We can only see where the atoms are. So while the electrons are still having a trigonal planar conformation, if I can't see that one, this molecule becomes bent instead of trigonal planar. So the shape at 2 shared, 1 unshared, they told you in the video, was going to be bent. And lone pairs of electrons are a little bit fatter than bonding pairs. A bonding pair of electrons, the electron cloud is being pulled this way because of the nucleus of the outside atom, and being pulled toward the center because of the nucleus of the central atom. So the cloud essentially ends up stretched out and long and thin. This unbonded pair down here doesn't have anything out here pulling on it. So rather than staying long and thin, it goes bloop and becomes short and fat. And when the non-bonding pair becomes short and fat, that puts a little pressure on these pairs, and the bond angle essentially folds in a little bit to make space for the fat pair that doesn't have a bond. So that was the 4th idea that came up here. Lone pairs of electrons need a little more space, so they push the bonds closer together, reducing the bond angles, and we're going to say by about 2 degrees per lone pair. So a reasonable estimate for the bond angle on this bent molecule is going to be 118-ish or so degrees. So if we go back to our other sheet here, our trigonal planar family consists of 2 possibilities. Either your molecule is trigonal planar, or we're missing this piece and our molecule is bent. And if you want, you can even put 2 dots up there to remind yourself that the molecule doesn't straighten itself out because this pair of electrons up here needs to have some space. And so the arms can't come up because they'd hit that lone pair of electrons. Okay, so that takes care of our trigonal planar family. Let's try our tetrahedral family. So within the tetrahedral family, possibility number 1 is that the spaceship is completely intact. All 4 positions are involved in bonding. The molecular shape and the electron geometry are identical to one another, and we have a tetrahedral molecule. The word tetrahedral comes from the fact that tetra means 4, and hedral means triangular faces. If you look at your molecule, you can see that it would have 4 triangular faces. And then one on the bottom here. Okay. So the word tetrahedral means 4 triangular faces, and that's how it gets its name. Now we can start pulling things off of this and seeing what we end up with. If we have 3 bonding pairs and 1 non-bonding pair, 1 lone pair, I can take that off. So remove 1 atom. And then if we keep in mind that the lone pair of electrons is invisible, what's left here is basically your spaceship with nothing but its pod feet. It's triangular, it's raised up in the middle, and we call triangles with raised middles pyramids. So now we need to try to draw this thing. Well, it's really just the tetrahedral one minus the top piece. So we're going to draw the same thing we had for the tetrahedron, but we're going to leave the antenna off. So here's the middle. Here's one leg sticking out at us, and one leg going back into the paper. Trigonal, and this one isn't planar. Planar would be all the way flat on the page. This is raised middle. Raised middle is pyramidal. And if we take our spaceship and we take one more of these things off, and so nothing here except a lone pair, and lone pairs are invisible, and we look at our molecule, now we're back to just having something that's bent again. So essentially just that much of our tetrahedron. So the other member of the tetrahedral family is the bent molecule. And if we want to remember why the middle stays raised up here, we can put the lone pair of electrons in there, because that reminds us that the feet get pushed down. And we can put 2 lone pairs on this one to remind us that the legs get shoved in on the bent. Now, while this version of bent and this version of bent have the same name, they are different in what they have for bond angles. This one, because it only has 1 pair of electrons, has a much, much larger bond angle than this one, because this one has to have room for 2 pairs of electrons. The more pairs of electrons you have, the smaller the bond angle is going to be. So if we go back to here, we know that if the answer to number of lone pairs is 0, electron pair geometry and molecular shape are the same. So this one should have come back tetrahedral. Unlike the trigonal planar one, where it's pretty easy to eyeball the bond angle and know what it is, this one is weird. A tetrahedron has bond angles of 109.5 degrees. There's not really a simple way to calculate that. You have to use some calculus and some spherical coordinates, so it's probably easier just to remember the 109.5. This one was our trigonal pyramidal. The little Ed puzzle gave you 107.3 degrees for the bond angle. I'm content with a little less than 109.5. You don't need to know an exact number, as long as you know it's a little less than 109.5. And this one was bent. I think the video gave you 104.5 as the bond angle. But I'm really content if you just know it's 109.5, a little less than 109.5, a little less than 109.5. The exact numbers aren't that critical because none of these three numbers are anywhere close to 118. And that's the difference between this bent one and this bent one. This bent one is kind of close-ish to the original 120 degrees, and this bent one is closest to the original 109.5 degrees. So you have two varieties of bent. One has a bond angle substantially smaller than the other because one has two lone pairs, one has only one lone pair. And the one with fewer lone pairs, that bond angle can open up a lot more because it has a lot more space. So depending on what representation you like best, here's one that has it kind of in a table with everybody bunched together. Here's one that's got things kind of drawn out more in a column looking a little bit more like your model kit. So two different ways to kind of represent those same ideas. In my mind, I actually operate from a mental image of these three shapes. Put my poor tetrahedron back together here. So I just have a mental image stored of these three models. And from those three models, I can basically, in my mind, start plucking the pieces off and looking at what I have left over when all is said and done. And that's the approach that I have found is most successful in teaching people to manage VSEPR theory. Here's what I consider to be the best set of steps for figuring out molecular shape. You've got to start by drawing a Lewis structure. Then you need to count the electron groups around the central atom, draw the electron group geometry, and then do that in pencil so that you can proceed to erase groups for the lone pairs. Okay? You don't get to use the model kit on your test, so we can't do the pluck it off. We got to have some way to kind of otherwise pluck it off. So we're just going to erase it and then look at the shape of whatever you've got left. If you flip this over, you'll find some examples on the back here. And we are going to work through a couple of those examples together. And then the rest of them are going to be homework. Okay, some ideas we need to bring with us. Always a good idea to have these magic words for electronegativity. They help us with our Lewis structures. So there's those. And important to recognize that the options for electron group geometry are limited to these three choices. So when we have to draw and name the electron group geometry, you only have these as options. And they are the linear, trigonoplanar, and tetrahedral. Some of you I know are going on to take Chem 105, and there are actually two more families that we talk about in that class. But these are the three most common, and these are the three that we're going to focus on for Chem 101. So let's try a couple of examples, starting with our NH3. Step one is to draw a Lewis structure. So nitrogen has 5 valence electrons. 3 hydrogens with 1 electron each. We're up to 8 valence electrons. Hydrogen has to go on the outside because it can only make 1 bond. So we're going to have to put the nitrogen in the middle, stick the hydrogens around the outside. That takes up 6 of our electrons. I've got 2 left. And it says if electrons are left over, stick them in the middle. So there's my Lewis structure. Now I count electron groups around the central atom. 1, 2, 3, 4. Then I grab in my mind a mental picture of something with 4 electron groups around the outside. So in my mind, I grab this thing. That's the 4 electrons group 1. And I'm going to say that that is tetrahedral because it has 4 electron groups. And I'm going to draw a picture of it. There we go. So the electron structure of this thing is tetrahedral. And now I'm going to redraw this thing. Like that. And I'm going to erase one of those because I have a lone pair of electrons. And I look at the picture of what I have left, and what I have left is basically a little tripod with a raised middle. Trigonal pyramidal. And people always want to know, why do I make you draw something if I'm just going to have you erase it in the first place? Because it stops you from jumping to the conclusion that because it has 3 arms, it's going to be flat. It reminds you that these feet have to be folded down because there's a lone pair of electrons up here that's taking up space. Okay, let's try one more. CCl2O. 4 valence electrons in carbon, plus 2 chlorines at 7 valence electrons each, plus 6 for the oxygen, grand total of 24. Least electronegative in the middle, so we have got oxygen, chlorine, and carbon. Carbon's way out here on the end. So with it being the least electronegative, we'll stick that one in the middle. Put everybody else around the outside. There's a chlorine. Here's a chlorine. There's an oxygen. And now I start for some electrons. We start filling up the outside first. That gets me up to 24. And then I don't have enough electrons on the carbon, so I'm going to take one of the pairs off the oxygen here. Move them to the middle. So there's my Lewis structure. Coming off the carbon, I have 1, 2, 3 electron positions. So out of my brain, I grab that one. And that thing is trigonal planar. Redraw it. Erase for lone pairs around the central atom. Okay, done. There aren't any. And I write down its shape, trigonal planar. Your homework is to finish the rest of this chart.